Real-time multi-object cross-view tracking. Let's show you the demo of the project first. In this demo, we have 3 cameras, each capturing real-time video flows. Our system is able to track multiple objects in real time, even when the objects cross the views. Here's another demo. In this demo, we show you the robustness of our system to variance of pose, lighting, and perspective. Next, let me show you the technical details of our project. This is the overall architecture of our tracking system. It's made up of 3 levels. The first level is a graphic user interface with which we could interact with our system. And there is a system controller which connects all the components of the system. And we have multiple sub-trackers. Basically, we have 2 cameras. But also, the system can be easy to be extended to multiple cameras. Then, how SUBTRACTION works. A SUBTRACTION is made up of 2 components. One is the ultimate moving object detector. Another is a real-time object tracker. Then, the ultimate moving object detector is based on real-time background subtraction. This method only works for stationary cameras, and the real-time object tracking is basically the tracking based on detection. In tracking based on detection, we need to train a discriminative model in real time. And the feature we use to train a model is adaptive color attributes. To increase the training speed, we employ the circular structure kernelized detector. Let's talk about the ultimate moving object detector. To detect a moving object, we employ a 3-step procedure. First, we process background subtraction based on Gaussian mixture model. And then, we detect the candidate by first process a morphological operation. This operation will eliminate most of the noise. And then we detect the blob and combine some blobs and finally filter the blobs. If we get more than 1 blobs, we need to select the primary candidate of the object by appearance matching. Let's look at the picture. First, we estimate background by Gaussian mixture model. When an object comes into the scene, we process the background subtraction and we get a blob map with a lot of noise. Then we process some morphological operation and using the blob detection, combination, and filtering to get a relatively clear blob map. What if we get more than 1 blob? For example, in this case, when an object gets out of camera 1, it enters the camera 2, and we process the moving object detection and we get 3 blobs. Which blob is the right one? We need to record the appearance of object in camera 1 and then match each blob with the appearance to see which one is the most similar. Finally, we got the right one by appearance matching. Here is the result. For real-time object tracking, we employ a 4-step procedure. First, we capture next frame. Then, we detect the object. Once we get the location of the object, we process dense sampling to get all the training samples from a single image patch. This is the positive sample. This is the negative sample. Once we have all the samples and labels, we got to train a new discriminative classifier by using the cost function like this. And we find the primary plane which discriminate the positive from the negative sample. This 4-step procedure is repeated at each frame periodically. In this way, we track the object in real time. Then, how subtrackers communicate. For example, we have a collider like this, and we put 5 cameras, which is responsible for each part of the collider, respectively. Only after the object exceeds camera 1, it enters camera 2. In this way, we build a so-called multi-camera adjunctive map and a system to help the subtrackers communicate. We use a multi-camera adjunctive map to record the adjunctiveness of cameras. And when an object exceeds the scene of camera A, it triggers the adjunctive camera, let's say camera 2, camera B, to process automatic moving object detection. Also, in this way, we could build a cross-view correspondence. Thank you for watching this video.